Next up will be Deborah Ferguson, speaking on testing general relativity with gravitational waves.
Just over a century ago, Einstein introduced the world to the idea of a black hole, a concentration of mass so dense that not even light can escape its grasp. Our universe is filled with these black holes, each out there spinning, dancing on its own. And Einstein described what it would look like if two of these were to collide. The collision would involve an in-spiral, during which the black holes are far apart, each spinning on their own, but also orbiting each other and getting closer and closer. Then, after billions of years, they would get close enough that they would merge and form one single, highly distorted black hole, which would then ring like a bell as it loses those distortions and becomes one single spinning black hole. And Einstein explains to us how we can take those two initial spins and determine that final spin. But how do we know if he's right, especially when we can't even see black holes? Well, remember how earlier I said that these are exceedingly massive? That means that throughout this entire process, they're violently distorting space-time. Think about an object moving through a pond and how it sends out waves in every direction. Well now, a century after Einstein came up with this idea, we have the technology to be able to detect those waves, thanks to LIGO, the Laser Interferometer Gravitational Wave Observatory in Washington and Louisiana. So, using their data, we're able to find that final spin and use it to test Einstein's predictions. But the question is, which part of the wave should we use to actually find that final spin? Einstein answers that with ring down, that last part of the collision, because the waves emitted during ring down directly give us that final spin. So in theory, that seems perfect. Unfortunately, we don't live in an ideal world, and so we have to deal with whatever the universe gives us. And the waves emitted during ring down are really small, so they can be easily overpowered by the sound of a car driving by or a bird pecking on the detector. So we can't detect it right now, and frankly, we may never be able to detect it. So what do we do? Well, it turns out that instead of using ring down, we can use the merger, because I found that it contains the same information that's available to us, specifically that final spin. And merger, the waves it releases are big, so we can detect it right now. And LIGO has detected it right now many times and expects to detect many more mergers. This means that right now, a century after Einstein developed his theory, we have the data to detect his theory now.